Okay, hello everybody. I'm going to talk about assignment 3 that I've posted recently. This is about kind of manually doing DES encryption algorithm that I guess it was a little bit tricky for some of you. I know that some of you have already done that assignment, that's fine. But for some of you that you may need a little bit more instruction on how to do that, here is the assignment. And we wanna do the DS encryption algorithm manually, which is of course is gonna be a little bit of maybe extra details, working with bits and bytes for probably 1 hour or 2 hours. Uh, but I would like for you and for the class to at least do this only one time for the DS encryption algorithm. And of course, for other encryption algorithms, I'm not gonna give you the same assignment. And I let me say this that kind of gives you an easier time. I'm not gonna even ask you the same question in any of the exam. I'm not gonna ask you to encode or encrypt or decrypt anything in the exam because I know it needs a lot of concentration and attention, and there is a very high chance for any of you to kind of do it wrongly. But what this assignment is asking you, it gives you a plain text, which is in hexadecimal. When we say hexadecimal, means that any of these digits basically should be represented as a 4-bit number. And then we apply it to the different steps of the algorithm, which is here. So we make the 4-bit representation of that number. We apply the initial permutation, and then we go and we only do one of the rounds. As we discussed in the class, there are 16 rounds for DS encryption algorithm, but we only do the first one, the first round. And here are the points that I want you to to give me the data. So after you convert your initial data into a 64-bit binary number, you perform the initial permutation on that. And what you get out of the initial permutation is what you submit in the point 1. If you open up the assignment on Blackboard, there are seven points that says enter the value at point 1 here. So what you get here, you enter it in the point 1 on Blackboard and just click submit, and then it's going to be kind of graded by the machine. So anyway, let's. I'm not gonna do the whole part of that because this is an assignment. I want you to do it, but I want to make it clear how you should be doing it. The first thing is looking at our plain text, which is a hexadecimal number, and try to convert it into binary. How do you convert the hexadecimal number into binary? Okay, there are two ways for that. You could do it manually using these two tables. This table tells you instead of every single 0, you should put 4 zeros. Instead of every single 1, you should put 3 zeros and a 1. 2 in hexadecimal converts to this number in binary. 3 converts to this, and so on. We go all the way up to F, which is 4 ones. This is one way you could do it. The other way, here is a link for an online hexadecimal to binary converter. So I just copy the text, I say copy, and I go to this link. Do you see my screen, Lalit? I've shared my screen. I just want to make sure that you see the screen, right?
No, I see the same screen. I see your
Oh,
instructions right now is all I see.
so you see the PDF file I shared with you?
I do see the PDF file.
Okay, great. So let's go to I'm gonna go to this page, and you see the online converter now, right?
Yes, sir.
Okay, so let's see how we can use this online converter to convert from hexadecimal, as you see, to binary. There are a lot of different things that this tool is able to do, but we only want to convert from hexadecimal to binary. So I copy the value I had in the assignment, which is here, 1, 2, 3, 4, ABCD, DCBA, 4, 3, 2, 1. I copy it and I paste it in this tool. and I say from hexadecimal to binary, and I hit convert. So it gives me the binary equivalent of that. But there is a trick here. If you see, it says 61 digit or 61 bits, which basically it is not what we expected. We expected to receive 64. The reason is for the very first or the very left number, this tool, it doesn't look this as a text. It takes this as a number. So it doesn't put zeros left to the number. So basically here we have 3 zeros which are not here. So if you copy this, if you're using this tool, you should be copying these. And let me open up my Word document. Yeah, if you paste it here, you should be adding 1, 2, 3 zeros. These 3 zeros, I've added them manually because like I said, this online converter puts only 1 for the first one, but we also need these 3 zeros. So this is one trick. So always make sure that when you're using this tool, you're converting 16 hexadecimal number and you are getting 64 binary digits. And that may only happen to the very first or very left digit because, like I said, it considers this as a big number in hexadecimal. It doesn't see it as a text or as a ciphertext or blah, blah. Anyway, we get this, we get our plain text. This is our plain text. And now we want to do based on the instruction, if you see, we want to do the initial permutation. So how the initial permutation works, you should go to the slides. If you go to the slides of the course for DS encryption algorithm, here is a slide that we are talking about initial permutation. The initial permutation is just doing some shuffling from the input to the output. Basically, it shuffles or randomizes the input data to the output data. So look here, this is bit number 1. I explained this in the videos as well, but I'm saying it again. The left bit, the most left bit, I don't want to say most significant because here we don't see them as a values. We don't see them just as a symbols or bits. The most left bit here is counted or indexed as bit number 1. And the most right one is labeled bit 64. So, but this table tells me that bit number 1 of input, it should go to bit 40 of the output. So what I do, you can do it using Microsoft Word or using Excel. I would say Excel is even better. I draw a table, let's say 60. I don't think it allows me to create tables of 64. So I say 63. I tried it yesterday. And here is my plain text. This is bit number 1, number 2, number 3, 4, 5, and so on. I don't want to count it for all the way. This is, of course, my 64. Let me change my layout to landscape so we get a bigger space. This should be 64, but these are not 64 cells. Anyway, and here is your input 0, 0, 0, 1, all the way to 0, 1, 0, 1. So let me change the color of the input to something. For example, our input is, how do I do this? Yeah. For example, my input is green and I make the output, for example, blue or something. So this table tells me, again, let's get back to the slide. This table tells me bit number 1 of the input goes to bit 40 of output. So whatever I have in bit number 1, which is 0, I put it in bit number 40, assuming here is bit number 40. So I here see 0. So I copy this 0, or I just look at it and I put it here. So I put 0 here. Again, getting back to the table, it tells bit number 2 of input goes to bit number 8 of output. So here is 6, 7, 8. This is the 8. Bit number 2 is 0. I put it here as bit number 8. So I look at this 0 here, this 0, and I put it here at bit 8, position 8. And I continue the same thing. 3 goes to 48, 4 goes to 16. Let's say if this is 8, 9, 10, 11, 12, 13, 14, this is 16. 4 goes to 16. 4 is 1, so I put 1 here. And this way you populate all the 64 bits for the output, which is blue here. After you populate all the 64 bits, you get a value, and that value is a number. Let's say you get something like this. I'm gonna just shuffle it in a little bit so that it represents. Let's assume that you get this number. This is your 64-bit. Also, I put it here. This is your 64-bit output. So what I'll be doing is that tool. Now we need to convert this into hexadecimal. You can do it manually, or you can do it. You can use that tool again. So if you want to do it manually, you need to separate it 4 digits by 4 digits, or 4 bits by 4 bits, and then try to convert it. So okay, and now we know that in hexadecimal this is C, this is 9, this is 0, this is 8. I know that table. You can look at the table. This is again C, this is 2, 8, 4, this is A, this is F, 7, 7, 2, this should be E, 9, and 0. Okay, sorry. And this is your hexadecimal number after initial permutation. I haven't done it. I'm just kind of making up some numbers. Of course, this is not the exact answer you should put on Blackboard, but after you populate all the bits, all the blue bits, you get something like this. You convert it into hexadecimal, and this is the value that you copy. It shouldn't have any of these dots. Forget about these dots. These are just Microsoft Word just put them whenever I hit the blank. So you copy this and you paste it in your Blackboard, and that's it. That's your you concat all of them together. So what you enter will be something like this: C908. I'm sorry, C908, C2 84, AF 772, E90. Yeah, this is your data after initial permutation. So you copy this, and this is basically what you're supposed to enter here in point 1. Now let's talk about point 2. Point 2 is talking about key. Of course, you need to know how the key is going to be generated. For that, again, we need to look at the slides. Key is going to be generated according to what we mentioned here, which is called round key generation. Round key generation. Again, you convert your initial key. You convert your initial key into a number, and then using these tables or following what we have, the details we have mentioned here, you compress the 56-bit key to a 48-bit, and you get that 48-bit key, and that's your key according to this table. And that's what you enter here. That's what you enter here as point 2. And then we have 0.3, which are here, your 0.3. For 0.3, whatever you have in your, after your initial permutation, you got the 64-bit number. That 64-bit number, we divided in two sections. We talked about this, the left side and the right side. The right side goes immediately to the left side of the output. So whatever you get in the right side after, or the right side of 0.1, that will be the left side of your 0.3, exactly, with no change. But the right side of your 0.3 is going to be tricky because it should be calculated based on the right side of 0.1 and the f function and the left side and XOR function. So for 0.3, you stop for 0.3 because you cannot calculate the right side of it at this time. So you calculate 0.4567, and then you can come back and finish 0.3. For 0.3, you do, yeah, basically here we are talking about the f function. You take the right side of your 0.1, the 32-bit, which means bits 33 to 64. When I say right side, it is bits 33 to 64. You take them, you apply them to the expansion D-box, and then here is this expansion D-box. Again, you look at the slides, you see how to expand them to 48. That's going to be your 0.4. And here is the expansion D-box. If you want to know, that's different with the key generation. So if you look at this slide here, slide number 50, we talk about expansion D-box that makes your 32-bit number makes it 48 bits. And the way it works is this: you apply the 32-bit, and here's you basically need to follow this table. Bit number 32 sits here, bit number 1 sits here, bit number 2 sits here, and so on. And of course, for expansion, you see some of the bits are used more than once. So bit number 1, it appears here and also appears here. Bit 32 appears here and appears here. So that's why we say that we are expanding from 32-bit to 48 bits. And that 48-bit that comes out of this table, that's what that counts as your value of your 0.4. Again, you convert it to hexadecimal before after. And then you XOR it with your key, that gives you your 0.5 value. And then you apply it to the SBox function, it gives you 0.6 value. And then you do a straight debug, it gives you 0.7. After you get 0.7, you have this right side as well. You put it next to the left side that you kind of initially got it from the 0.1. You make your 64-bit, and then it kind of together they'll be your value at 0.3. So this is how basically you're supposed to do. And I know that it needs a lot of concentration, but I believe that it is very good, but because it shows you how encryption algorithm works and how it is important to pay attention. Because if you mess with one of the bits, especially if you do it initially in one of the earliest stages, you'll be getting a totally different number at points, for example, 6 or 7. So I guess this should be a little bit kind of, this should give you a little bit insight about how to do this assignment. Again, I would recommend doing it something like this in a Word, or better, even better than Word is Microsoft Excel, open or Google Sheets. It doesn't matter. You don't have to have Microsoft Excel, but they allow you to count the bit positions and kind of follow them one by one, so that you make sure that you don't do anything wrong. So if there is any question from audience, please ask. So I can answer for everybody.
Okay, so I think I followed you. So point one is the IP config. After
Mhm.
you've done the initial point two, that's the PC1. Is that correct? The key where you've
Yes.
brought the key down. Okay.
Mhm.
I was listening, but I was trying to listen to you and write stuff at the same time.
Yeah,
Um,
that's fine.
go ahead.
And like I said, the meeting is recorded, so I'll upload it on Blackboard again. And
Okay.
again, I didn't want to mention this kind of openly, but I saying it that you don't see such thing in the exam, but I don't want to kind of you miss this opportunity to at least dive into one of the encryption algorithms, because this is very important to know how they work exactly. Of course, you may not remember all of these things after you've done this assignment. I completely understand this. Even for me, that I've been doing this for a long time, I need to look at those tables. But it gives you a very good insight how the encryption algorithm works. And when someone talks about, for example, substitution box, now you know what the S boxes are and why they're important, or expansion debug, why they're important and what's their role. That's why I believe it is good to do this assignment, although it might take time. But just talking about encryption algorithm, it doesn't give you the enough kind of insight, I would say, unless you kind of take the pencil and paper and pencil and get to it and try to do it manually.
Okay. It's been interesting.
Yeah, of course, it is a very interesting area of research. People talk about uh, design of S boxes. There are a lot of kind of information theory research and, let's say, science behind how to create only S boxes. The S box is very important. If you change the S box, the strength of the encryption algorithm may change. You may lose, or you may kind of enrich it. But there are a lot of discussions behind that. For example, Galois field, information theory, entropy, stuff like that. It, of course, it's beyond the scope of this course. But if we know what are the S boxes and how they work, later, if you're exposed to such information, you may have a minimum understanding what they mean and what their impacts are. So
Okay.
if there is no more question, I'm gonna stop recording. And as a latest kind of update, I have also changed the due date for this assignment. I've postponed it to the 6th, so you would
Okay.
have extra more time to work on these. And feel free to reach out to me anytime if you have any question. Email me. It's completely fine if you email. I would be happy to answer you anytime.
Okay. Thank you so much for meeting with me today. I feel like I have a better understanding of where I've been messing up at.
Thank you for asking for this, and I'm happy that we have done it. Thank you.
All
Have
right.
a good rest
Have a
of the
great
day.
day.
Bye bye.